This is a lecture to introduce you to nuclear magnetic resonance spectroscopy, or NMR as we usually call it for short. And there are a number of atoms that can be studied using NMR. In particular, two that are very important to us at this point are hydrogen 1 and carbon 13. And I'll talk to you a little bit about why that is as we go through this short lecture. First, though, I want to tell you what NMR can tell you, at least proton NMR or hydrogen 1 NMR can tell us. So it can tell us what hydrogen atoms are next to in a structure. So if you're near pi bonds or you're near electronegative groups, if you are an acid hydrogen, NMR can actually tell us a lot about what environment the hydrogens are in. So if you think about a chemical structure, for example, like an alkene or an alkyl halide, those characteristics of the functional groups, or the characteristic functional groups, have an effect on the signal that we get for hydrogen atoms in those structures. And we can see that, and that can help us piece together a puzzle that tells us what the final structure could be for an unknown compound, and also verify what our product is in a synthesis reaction when we produce a product and we want to verify whether or not we have the correct product. Another thing that it does, and is very useful for, and this is part of the puzzle piecing together, is it for every type of hydrogen that we see, that for every type of electronic environment that we see, the hydrogens talk to each other like they're neighbors. And what ends up happening is the NMR signal for a hydrogen will actually tell us the number of hydrogens that are next to it in most instances. So if you know, for example, I have one neighbor and my neighbor has two neighbors, you can kind of piece together that my neighbor is between two people on the street. And that's kind of the idea with how we use this information. It's kind of to develop a sequence to know which neighbors are next to each other. When neighbors talk to each other, they talk to each other different amounts, and because of that, we can use that information to piece together a simple structure for many compounds, just using NMR spectroscopy. The other useful thing that NMR spectroscopy does for us is it tells us, of all these talking hydrogens, it tells us how many of each type we have. Now, it's kind of like an empirical formula, though. It doesn't tell us exactly the number of hydrogens we have. It tells us the relative numbers of hydrogens. So, for example, in an empirical formula, if you think about glucose, which is C6H12O6, its empirical formula is just CH2O. That's the kind of information that NMR will tell us. And so it turns out that information is a lot more useful in NMR spectroscopy because we usually have a molecular formula or a molecular weight of a compound, and then we use that relative numbers of hydrogens to help us piece together again what the structure of the compound is. I want to be very clear, when you look at NMR spectra, it doesn't say to you, oh, that's what this structure is. It says, these are the pieces, here, you put the puzzle together. And we use a lot of different techniques to help us piece the puzzle together. For example, you could tell a hydrogen is near an electronegative group or perhaps near a pi bond, but there's all kinds of functional groups that have pi bonds, and there's all kinds of electronegative groups. For that kind of analysis, we typically rely on IR spectroscopy, because IR spectroscopy tells us a lot about what kind of functional groups are in a compound, and not as much so about the organization of those functional groups in a compound. Another big piece of information that we can use, and we'll cover this later this semester, at least preliminarily, we will be talking about mass spectroscopy. And in mass spectroscopy, you can break a molecule down into groups of related atoms, and from those groups of related atoms also use that information to piece things together. For the most part, however, NMR and IR are really all that you need in the first semester of organic chemistry to piece together what a compound is from its spectra. Okay, so imagine you have a guitar, and the guitar represents a molecule. And so the molecule is in its chemical environment, and then we hit it with a large electromagnetic pulse. Now, in this case, to illustrate an electromagnetic pulse, I used a hammer. When the hammer hits the guitar, what's going to happen is noise is going to come out of the guitar. Now, initially, there's a lot of noise, but as it turns out, as time goes on, that noise dampens, and what you begin to hear is only the resonant frequencies of the molecule. So let me freeze this and talk about that for a little bit. So imagine that you have a molecule, and perhaps it has this structure, and just making up a structure. Let me go back to, I have a white pen, let me go to a black pen. So perhaps it has a structure like this. And keeping with, seems to be my favorite molecule this semester, 2-bromobutane. On this compound, there are a number of different hydrogens. This is a CH3 over here. This is CH2. This is CH3. Now, each one of these is in a different chemical environment, and it turns out the spectra for those, the spectral response for each of those will be slightly different. Now, if two hydrogen atoms are exactly the same, then what ends up happening is those signals will merge together and produce only a single signal. You'd expect this in molecules that have symmetry, and there's a couple of rules that help us do this that we'll use later, where we look at the symmetry of molecules and the symmetry of actually the hydrogens on molecules to determine whether or not the signals are going to be the same or different. But in this case, we will definitely have 4 different signals. The 4 signals that would be coming out, though, in this sort of analogy, when you strike the molecule with an electromagnetic pulse, there's all kinds of crazy energies that will be coming out of this molecule. So you could expect just a lot of noise to come out. This is time on this axis. And on the vertical axis, we just basically have energy. And we're recording the signals for all of these different vibrations that are going on at the same time once the molecule has been struck. Now, if you know how guitar works, each of the strings is tuned to a particular note. And if you hit a guitar like that, it makes a horrible noise at first, but if you listen closely, eventually what you get is the signal for all 6 strings coming out at the same time. In the NMR spectrum, what you would end up seeing is you'd see what's a complicated waveform that begins to go like this, and you'll see repeating patterns in that waveform. We use a technique called Fourier transform, and in the Fourier transform we take this frequency-based data, or sorry, time-based data, my bad, and we convert it into a frequency-based data. If there are really just 4 signals in this compound, what we expect to see is 4 different signals based on the energy of each. The relative area under each of those lines would be representative of the number of hydrogens in that compound. So before we begin, so that's sort of the basic premise. What we do is we hit the sample with an electromagnetic pulse. That pulse causes a lot of energy to be absorbed by the molecule. Initially, that signal that comes out is very random and noisy, but if you wait a short amount of time, then eventually you begin to see the harmonic frequencies of each of the hydrogens in that compound, and then we use a Fourier transform to convert that over to the frequency domain. And in the frequency domain, that's what we call our NMR spectrum. Now, to simplify this whole thing, we typically convert that frequency domain into a unit called parts per million. And unusually, as is many times is the case in spectroscopy, 0 is on the right-hand side. And to the left is where we plot all our signals. And typically for hydrogen NMR, this can go up to about 15, but is typically less than 10. Okay, so let's look at some of the things that influence the NMR signal. So again, just a kind of an overview. Hydrogen atoms, well, think back to electrons. If you remember, electrons have magnetic moments. We call it the spin quantum number. It turns out that means the spin quantum number means that the electron has two different magnetic moments that it can have. And we call that plus a half and minus a half, because and we call it a spin state historically because we visualize spinning electric charges, and a spinning electric charge will generate a magnetic field. So we would say spin up or spin down, but really what we're talking about is the magnetic field of the electron. So electrons have magnetic fields. If you take electrons in atoms, for example, that have different spins, and you run those atoms through a magnetic field, you can actually see the atoms separate into two different groups depending on which way the electrons are spinning in the atom. The last electron, as it turns out, is spinning in the atom. This is a very famous experiment. If you want to look it up, it's Stern-Gerlach or Zeeman effect. If you look up either one of those, you'll find the information on that. So now, turns out hydrogen atoms with just a proton, so H1, has a magnetic field. And so if you take and you put a hydrogen atom in a magnetic field, you develop two different spin states. Now, in a magnetic field, what the hydrogens want to do is they want to go into a low energy state. And they like to be down here. And you'll notice this is spinning parallel. The magnetic field is parallel to the magnetic field. That's the low energy state. When you pulse the atoms, some of the atoms' spin states will invert. Now, I don't really know if the hydrogen atoms actually flip over. That is, the nuclear particles actually flip over. But we know that they go into a higher spin state with a inverted magnetic moment. So, inside that atom, then, you have this high energy, and like you saw in the Bohr atom when you studied Chem 1A, stuff at high energy wants to eventually come down to the low energy. These energy states are quantized. So there are only specific energies that can be released, and that's going to depend on a number of different factors, one of which is under our control, is the magnetic field. So input energy, we put the compound in a strong magnetic field. We input energy. We get excitation and emission. In the first part that we get a lot of noise coming out, but eventually we get the resonant energy, and the resonant energy comes out at the frequencies of the atoms that are, or the hydrogens that are in the molecule. Okay, so resonant energy then is analyzed for information like the number of hydrogens, the number of neighbors, and the electronic environment. We can control the magnetic field. That partially controls how big the split is between the high and low spin states. So, we're talking about nuclear spin, so I know I mentioned electron spin, so hopefully it doesn't confuse you. We're talking about nuclear spin, and really what we're interested in, and it turns out like hydrogen 1 and carbon 13 both are NMR active elements or atoms. Hydrogen is 99.99% H1, and that's great because every compound that we have in organic chemistry has some hydrogen in it, and it is all NMR active, except for that 0.01%. This means the signal that we get for hydrogen is very strong. Turns out carbon-13 has a relatively small magnetic susceptibility, it has a weak magnetic moment, and it's also only 1% carbon-13 of all the carbon that we have, like when we take a random sample of carbons. That means when you take 100 molecules, that's 100 carbon atoms, you'll for sure have at least one carbon-13 in that structure. There's only a 1.1% chance that you'll find a carbon-13 in a structure, and we'll actually use that information to our advantage when we do mass spectroscopy as well. So the signal for carbon-13 is weak. The signal for hydrogen-1 is strong. When we do NMR spectra of hydrogen, it's very easy to get a spectrum. When we do carbon-13, it's actually relatively difficult, but not impossible. It just takes a lot longer to collect enough signal to get a usable spectrum. So one of the things I mentioned is that an electron, a hydrogen-1 or proton has a spin. But we also know that when you have a proton in a structure, you also have electrons. And the electrons turn out to create a shield around that proton. So if you take an electron, a hydrogen atom, and you put it in a magnetic field, the electron spin creates an opposing magnetic field that reduces the magnetic field strength that the proton experiences. So let me say that again, maybe a little clearer, because I know I kind of bumbled through that. When you have an external magnetic field, let's say it's this, the electron cloud around the nucleus creates an opposing magnetic field, and that opposing magnetic field partially cancels out the magnetic field experienced by the proton in the center. As a result, the signal that we see will be shifted to different energy, and I'll talk about how that works in a little bit, but it gets shifted to a different energy because it doesn't experience as strong a magnetic field. So let's think about this. If the strength of the magnetic field determines the separation in the spin states, that is the low and the high spin state, and we cancel part of that magnetic field, there's less energy between the spin states, between the low and the high spin states for the proton. So what this means is it's going to shift the signal to a lower energy if you have this shielding electron cloud around the nucleus. So just very quickly, going back over some of these parameters, this beta, or this gamma, is the magnetic susceptibility. That's this. And you can basically ignore that, but it's different for every type of nucleus. But B is the external magnetic field. E is the energy between the low and the high spin states. Okay? So if B is large, this separation is large. Now, why might you want to do that? Well, if you have a lot of different atoms, the bigger you can make that gap, the easier it will be to resolve different types of electronic environments from each other, just because the energy separation is larger. In most modern NMR instruments, this number, they make it as high as they can. Let me go back. I didn't mean to switch the slide. This B, this is how strong the magnet is. They make this as large as they can to get as large a separation as possible over here. Again, if you cancel part of the magnetic field by putting an electron cloud around the nucleus, then delta E gets smaller. And we use that information based on, we have to have some landmark values, but we use that information to determine what kind of chemical environment or electronic environment that particular hydrogen is in. Okay. Some terms. We have upfield and we have downfield. So let me draw an NMR spectrum for you, just the axes. What we'll have on the y-axis is just intensity, so we're just going to call it I for now. And on the x-axis, we're going to have frequency, and it's going to be in units of parts per million. And again, I'll explain parts per million a little better as we get along, but for now, just remember that this ppm is related to delta E, and that's related to resonant frequency. Oops, spelled that wrong, sorry. And remember, we put 0 here, and then we put larger energies over here. I did 15 before, but you don't see that as often, but 10's pretty common on this end. So we have more shielding up here. This is small magnetic field side. And this is large B. It also represents larger resonant frequency and smaller resonant frequency. So, small magnetic field means high electron density. We call this the downfield side. Oh, sorry, upfield side. And this is known as downfield. So if you have less shielding, the separation is larger, you're shifted further to the left. If you have more shielding, your separation is smaller and you're shifted more to the right. And I just realized on this slide I should probably flip those things so they make more sense. But that's sort of the idea. So if you look at NMR signals, one of the things that we like to do is we like to have a solid reference point for our NMR signal. It turns out magnetic susceptibility and magnetic field strength are highly dependent on temperature and in little details about like how strong the magnetic field actually is. We'd like to say that we could control like the strength of a magnetic field very carefully, but it turns out we have a limited capacity to create an exact magnetic field. So what we do in every compound that we run, in most compounds that people run, is we put in a reference signal. That reference signal is generally TMS or tetramethylsilane. So if you think about carbon versus silicon, carbon's more electronegative. So what ends up happening is the carbon tends to pull electron density from the silicon, and as a result, those hydrogens on those methyl groups are highly shielded from the magnetic field. That means they're almost always to the far right of our compound. There are a few other compounds which are much harder to make, and also more expensive to use. You can shift even further to the right, but TMS is relatively easy to get in high purity, gives a strong NMR signal, and is generally the furthest peak to the right on the spectrum. So when we put TMS in the sample, we typically call that 0 parts per million, and then all the other compound proton shifts that we see are relative to TMS being equal to 0. It turns out when you do it like this, and you do the calculation of field shift for different compounds, if you represent the field, the shift in parts per million, the shift for every kind of carbon will, or every type of hydrogen environment will be the same relative to TMS. And that's independent of the magnetic field. So if your magnetic field's a little stronger or a little weaker, your parts per million shift will always be the same relative to TMS. So that's actually very useful. Your spectra will look slightly different if you have a stronger field. You usually get more separation between your groups. But in terms of position of the peaks, the position of the peaks are the same whether or not you have a 1 Tesla or 2 Tesla magnet. And if I remember right, I had to go quickly look it up. Tesla is the unit for measuring magnetic field strength, abbreviated T. All right, so here's a sample signal for acetone. This is known as a free inductive decay. We usually don't measure the first bit of this, and then we measure typically about 8 to 10 seconds worth of the free inductive decay, sometimes longer, sometimes less. On our instrument, we typically measure about 8 seconds of decay time. And that signal, that's this FID, this is kind of what you would see if you take the Microsoft wave file player and you see these funny little waveforms on the screen. This is essentially the same thing. And then we take that and transform, do a Fourier transform, and we turn that into frequency domain. And you'll notice that even though the signal is getting quieter, that is smaller, so in your ear, if you were to listen to this in a frequency range which you could hear, it would sound like it's getting quieter. It's all composed of a single frequency. A little bit of width here because it's not entirely a single frequency, but it's very close to a single frequency. So now, again, we got rid of the first part. This is the energy decaying, the resonant frequency leaving the sample, and eventually this will go back down to 0, in which case then we could pulse it again and we could look at another spectrum coming out of the sample. All right, so here's kind of a simple-ish compound. This is tetramethylpentane. The NMR signal for it is shown at the bottom. Again, you'll notice the units are in parts per million at the bottom. And you'll notice a couple of different things. CH3 groups have a characteristic resonant frequency of about 0.9 parts per million. That would be this signal here. The methylene group, so this group here, these groups have different names that we use in organic chemistry. A CH2 is a methylene group, just like methylene chloride, which we've used a lot of this semester. This is what you know it as a methyl. And then if it only has one hydrogen on it, like this, and there's not one of those in this compound, but this is known as a methine. So it turns out characteristic signal for like a benchmark or placement of a methyl group is 0.9 parts per million. Doesn't range too much from that, but it just depends a little bit on what that those carbons are attached to. Since they're attached to other carbons, in this case, the hydrogen signals that come from the methyl groups are around 0.9 parts per million. The methylene group varies a little bit more. It's got a little bit more stuff around it, but typically it falls in the 1.2 to 1.4 range. It could be a little bit on outside of those, but typically that's where you get it. And the methine you typically see up to around 1.7. So we don't have one of those in this compound. And so actually you could look at the spectrum and see that it's relatively simple. And that's giving us that actual information. There are no CH groups in this compound. Now, another thing to consider is the area under this peak, and it doesn't show it on here, but you can see that the area of the peak on the right is probably going to be a lot larger than the area on the peak on the left. So the methylene signal is much smaller than the methyl signal, and in fact, it's about 9-to-1. Again, the NMR instrument will give you that information, that 9-to-1 information. That's an indication of the relative number of hydrogens in this compound. You'll notice there are actually 18 methyl hydrogens and 2 methylene hydrogens. That gives us the ratio of 9-to-1. We usually do this as a graphic integral. That is actually a graph of the integration of the signal. But sometimes instruments, more modern instruments, and ours will do both, will give you both the numeric integral as well as a graphic integral that you can measure with a ruler. Here's another interesting aspect. Remember we talked about electronegative groups being able to shift hydrogen signals. So if you have a methylene group next to an oxygen, in fact, if you have any group next to an oxygen, the shift is typically about 2.5 parts per million. So if you had a methylene group, you could say, for example, methylene group, if you're saying it's about 1.2, oh gosh, sorry, didn't mean to do that. If it's 1.2, here, the shift is going to be about 2.5. You'd expect to see that signal around 3.7 parts per million. Oxygen of an ester, now remember, an ester has 2 electronegative groups. It's this one and this one. The first order, the closest methylene group was going to be affected by that oxygen the strongest, but because this carbonyl group is further away, it has an effect on these, but because it's further away, it's not as strong. So this is going to be about +3, and then for carbonyl groups, it's only about +1. So how might we do this and give you an example of what spectra might look like? This is 2-methoxypropanone, and I picked this compound, 1, because it's relatively simple, and 2, because I could steal the spectrum very easily from a website. So I stole the spectrum from a website. I believe the reference is in the footnotes of the slide. So, has a methyl group, has 2 methyl groups, and it has a methylene group. So if you take this methyl group and you say to yourself, I expect to see it around 0.9. It is next to a carbonyl, so I will add 1 to it. I expect to see it around 1.9. That's about where you see the signal. It's a little further than 1.9, but it's in that ballpark. For this methyl group, it's next to an oxygen, so it's 0.9 plus 2.5. I expect to see it around 3.4. It's actually around 3.3, but that's a pretty good first approximation of where you're finding these peaks. The one that's furthest off is the one where you have to add all these things together. And again, there are assumptions in like how much offset you expect to see, but you expect this to be 1.2 to 1.4. I typically use 1.2 as a first approximation. 2.5 for being next to an oxygen. 1.0 for being next to a carbonyl group, because it's next to both the oxygen and the carbonyl group. So predicted 4.7. It turns out it's only about 3.9 in the actual structure, but it gives you the idea, at least, that these signals will be separated by a large amount and kind of gives you a rough idea of where to find the peaks in the sample. Again, if you look at the integrals, and now this is what I mean by a graphic integral. This represents the integral of this peak. So if you take a ruler and you measure from here to here, and then you take and that will be proportional to the area under this peak, and you take the area, a ruler, and you measure from here to about here, where you see the integral stops getting larger at this point because the area the peak is going, the change in area of the peak is getting much smaller at the baseline down here. So this represents, oops, I touched the slide with my hand, sorry. This represents the relative area of this peak, and then this represents the relative area of this peak. Now, if you just look at the integrals and you know that it's 3 to 2 to 3, and you follow the arrows to make sure you're doing this correctly, this signal is about 2/3 of this signal and 2/3 of this signal. The area, that is the integral, is proportional to the relative number of hydrogens of each type in the compound. So that can be very useful in determining the structure. And you could have probably, with this information now, if I give you a similar structure, be able to piece together what the structure actually looks like based on offsets, where you see each of the signals, and the integrals based on the number of hydrogens. A couple other common offsets. I did this. These are simulated NMR, so they're a little cleaner and a little more predictable. But just to give you the idea, there was a methyl group. There's a pretty large shift when you have a chlorine on it. It's actually, with 2 chlorines, it's around 5.5. We very often see methylene chloride in our samples, and it's a peak that shows up way over here somewhere. Bromine, the shift is less, and iodine, the shift is even less, and that has to do with the electronegativity of the atoms that are attached. Low electronegativity atoms have smaller electron withdrawing power. As a result, the hydrogens in the chlorine are much more deshielded and shifted downfield, and the hydrogens in the methyl group are much less deshielded, so they're not as far downfield. So in comparison, the methyl iodide hydrogens are upfield from the methyl chloride hydrogens. The next effect takes a little bit of explaining, and if you don't understand how this works, it's okay, but you gotta believe that this is the way it works. This is important information, and I'm going to try to explain it the best I can, and then hopefully you understand it from that. But at the very least, you should be able to apply this information to spectra to be able to determine structures. Okay, so this effect is known as anisotropy. And anisotropy is when the magnetic field changes as a result of a locally induced magnetic field. So, how do you get a locally induced magnetic field? Remember, if you take a structure that looks like benzene, so here's benzene over here. Remember, it has pi bonds, so there's a double bond here, a double bond here, and a double bond here, or a double bond here, here, and here. And we draw the circle to indicate that it has resonant structures. Well, that pi electron cloud is above and below the ring of the benzene ring. When a magnetic field is applied to this structure as it comes up through the center of the structure, remember we talked about electrons producing a counter-magnetic field. Well, magnetic fields, if you've ever played with magnets and magnetite, magnetic fields are always closed-loop systems. That is, if you have a magnetic field in this direction that's being generated, it has to close on itself and come back around like this. And I could show you that if you want to in class sometime. But it's very easy to demonstrate that magnetic fields are closed. So, or magnetic field lines are closed. So here I have a magnetic field that's being generated. This magnetic field line is going around in a circle like this because it has to be closed, and it comes back through the center, and it loops around like this. Okay. Now, if the magnetic field is being induced down the center of the structure is, let's say, a 6 parts per million offset, just arbitrarily, that means on the center, the magnetic field is weaker, but on the outside, the magnetic field is stronger. So as it turns out, by having the magnetic field generated in this direction on the center of the loop, it's going to be stronger experienced magnetic field by this hydrogen on the outside of the loop. This same effect happens on pi bonds, like on double bonded carbons, on the hydrogens surrounding the pi bond. So what do we see? Well, if this was really a methine group, you'd expect to see it around 1.7. It's a CH at this structure, because remember I didn't draw those hydrogens. So if it's really around a 1.7, and that's where you expect to find it, you'll notice that it's all the way out here around between 7 and 8. And typically when you see a signal between 7 and 8, and that, in fact it goes a little bit to the right of 7, but between about 6.5 and 8, you're pretty certain that that structure has a benzene ring in it. It's usually fairly unique. Now 5.25 is what you expect to see for example, ethylene. There's a number of things that can be in that range, but typically if you think you have a double bond, you would see these hydrogens in the IR spectrum just to the left of 3000, and then you would also expect to see then, if you have that, signals between 5 and 5.5, maybe 4.5 to 5.5 parts per million. So those are offset quite a bit, and this effect is known as anisotropy, that is an locally induced magnetic field. So here's some typical shifts. I'm not going to spend a lot of time on this, but you can see, for example, when I was talking about alcohols, the H on an alcohol is typically found around 4 to 5. And so that's pretty close to an alkene. But if you had an IR spectrum, you had to distinguish between the H of a double bond, a vinyl hydrogen, versus the H of an alcohol. Well, you would very clearly see a large signal around 3400, a broad signal if it's a hydrogen bonding, or 3700 if it's not hydrogen bonding for this guy, and definitely this would not have that signal out there, but it would have that sharp signal that we expect to see just to the left of 3000. Okay? Again, different types of functional group neighbors have different effects, so just keep that in mind. I will be giving you what's known as a correlation table when we do this on our next exam to do structure analysis. Here's another table. Feel free to look at that table from the last textbook. I'm not going to spend much time on it. Again, I'll be uploading these slides to Blackboard. And here's yet another way to look at correlations. I like this chart probably the best because it gives you a range. The only thing that I wish it would have, again, I stole this from Michigan State University's virtual chemistry textbook, organic chemistry textbook. I wish what it did have is actually a line in the center where you find most typical compounds. But they give you the full range, and sometimes that can be a little misleading. So to see an alcohol, for example, at 0.9 is pretty rare. Typically it's up in this range here. So I wish they would fix that, but I may have to just remake the slide myself. Okay, so that's the introduction. I will produce another couple of videos on how many peaks you see, and then how do you know how many neighbors of peaks you see. Sorry. The next video will be on how many peaks you expect to see, and then the video after that will be how do you know how many neighbors a peak has, how many neighbors a hydrogen has, based on the number of peaks you see. And then finally, we'll put it all together with a worksheet in class where you do just hydrocarbon NMR and try to determine what the structures are based on empirical formulas and the NMR signals.